Hello class. So, due to popular demand from your teacher, Mr. Briscoe himself, who's been begging me for days to continue making these videos, because evidently he knows I'm a better teacher than him, I guess. For his sake, I'll keep making these videos for the time being. So today we're going to be talking about geometric isomers. So being isomers, they're going to be molecules that have the same number of atoms and bonds as one another, but they ultimately differ to one another in their spatial arrangements due to the presence of a double bond. It can also be a triple bond, but for the sake of VCE, we're just going to be focusing on double bonds for today. So prior to this lesson, you might think that these two butene molecules would or are essentially the same as one another, just like these two butane molecules. Although that may be the same for the butane molecules, it is, however, not the case for the butene molecules. From what we already know, the presence of a single bond allows the molecule to be rotated freely, and hence this branch, or this side group, or whatever you want to call it, can be rotated easily to fit the orientation of this group, hence meaning that these two butane molecules are essentially the same. And for my math nerds out there, you can sort of think of it as a reflection in the x-axis just for this part of the molecule. However, with the presence of a double bond, this reflection cannot be achieved because, and therefore, this side group is ultimately fixed onto the same side as this group around the double bond, and this side group is fixed on opposite sides as this group around the double bond. We also have a special way of naming these type of molecules. So as you may already know, for molecules with their functional group on the same side as one another around the double bond, we call them cis isomers, and for molecules who have their functional group opposite one another around the double bond, we call them trans isomers. So cis and trans just means this side of and other side of in Latin, if you in case you were wondering. So in terms of the general questions they will ask you about these type of isomers, it will mainly be about a comparison between their chemical and physical properties. Mainly physical, as they tend to be pretty similar in their chemical properties, but they again mainly differ in their physical properties. So as an example, you can see through the dipole diagram that I've drawn here that there is a net dipole movement downwards in this case for cis isomers. And however, for trans isomers, the dipole movement is in opposite directions to one another, and hence they cancel out, resulting in no net dipole movement. And this therefore results in the trans isomer to be non-polar in the case of butene, and a bit more polar for the cis isomer. Um, but obviously, having said that, forget what I've just said, because Briscoe obviously doesn't want you to overthink these things. Just remember that, using butene as an example, obviously, that the trans isomer tend to be non-polar, whereas the cis isomer is a bit more polar. So obviously, the difference in polarity can be applied to something such as a difference in their solubility. Um, for if we take water as a solvent, then the cis isomer is going to be a bit more slightly soluble than the trans isomer due to its greater polarity. Obviously, for the case of butene, this difference isn't going to be a lot, but it's nevertheless still a difference. Now, onto the more important physical properties. You need to know that the cis isomer tend to have a higher boiling point than the trans isomer, and the trans isomer tend to have a higher melting point than the cis isomer. Now, okay, let's get on to discussing the cis isomer. So, as I've discussed before, the cis isomer has a net polarity, and therefore it can also form dipole-dipole bonds, or dipole-dipole interactions, I should say, on top of the dispersion force that trans isomers can also form. And hence, therefore, being able to form stronger forms of intermolecular force, it therefore makes the total strength of the intermolecular force of the molecule a bit stronger. Hence, it takes more energy to break the bonds, and therefore resulting in a higher boiling point for the cis isomer. However, for the trans isomer, since it doesn't have a net dipole moment, it is not nonpolar and therefore can only form dispersion forces. But it has a higher melting point because melting point not only takes into consideration the intermolecular forces present, it also takes into consideration the structure of the molecule. So if we connect the carbon atoms on the trans isomer, you can sort of see that it makes sort of like a beach chair shape as opposed to like the table kind of shape of cis isomers. So this being a bit more symmetrical or linear, you can say that it packs together a bit more compactly and hence forms more extensive dispersion forces, therefore making it less likely for them to separate from one another. Because remember, melting point is not the breaking of those bonds, but the weakening of those bonds so that the molecule becomes a liquid state. So, for example, here you can see that I've stacked these molecules together, and you can see these tend to fit a bit more compactly than, say, if we had these molecules which, you know, don't fit as compactly. So, in a nutshell, that's basically just an introductory lesson on geometric isomers. I'm sure Mr. Briscoe has more to teach you, and you can obviously get a lot better at this through doing questions. So good luck at doing that, and I'll see you in my next class, I guess.